There was an old, wise woman traveling from Odessa to Minsk, traveling in an old rail car that long journey. As she traveled, she would speak to the other passengers, and they would listen. For the passengers from Pinsk, she spoke of the evil eye, how looking ill on others harmed the world. For the passengers from Bialystok, she spoke of the evil tongue, how speaking ill of others harmed the world. For the passengers from Lublin, she spoke of the evil ear, how listening to ill of others harmed the world. As so it should happen, when the train stopped in Kiev to take on a load of passengers, a young man embarked and sat down opposite them. Not knowing the identity of the wise woman, he began to speak of his journey. I am going to Minsk to hear words of wisdom from the great sage. I am told her words are golden, her speech viscous with insight, dripping with morsels of erudition. The wise woman, not wishing to be haughty, demurred. Ah, the great sage is nothing. Pay no heed to the stories of her. They veil the ordinary in drab and fancy. Taken aback, the gentleman slapped her full on the cheek. How dare you besmirch her name? Hours of silence passed between them, until finally the train arrived in Minsk. The next evening, the wise woman stood at the pulpit in the old shul of Minsk. Again, she declaimed the perils of the evil eye, the evil tongue, and the evil ear. But into her words cut the sound of a man sobbing. There, among the throngs, was the man from the train. Bring him to me, she said, and he was brought. Tell me, why do you weep? I weep for I slapped you, the very sage I sought to hear. Weep not. It is I who should weep. For you taught me my own lesson. An evil eye, an evil tongue, and an evil ear do as much ill when we look ill on ourselves. How can we seek to improve the world and improve ourselves if we do not first think well of ourselves? And that day, every student from Minsk to Melbourne learned to trust and treasure themselves, to believe in their worth, and to believe in their future success. Good afternoon, everyone. Now that we're coming close to the end of semester, I wanted to share one or two words with you. So I know many of you have put a lot of effort into this class so far. Some of you are finding it to be something that you kind of get after a fair bit of work, and others of you are finding that you're still getting to having a lot of challenges and having to spend a lot of time to kind of make the material make sense for you. And I just wanted to remind you how important it is that you remember the lesson from the very first class where we said that it's not about ultimately like, are you a star programmer at the end of the class? It's about how much you've improved on yourself. And I know for each and every one of you in this room, you have improved substantially. And don't think that computer science isn't for you or that you're no good at it just because you're not all the way at a 99 out of 100 right now. Just like the wise woman from the story that we just heard, it's really important to talk about yourself in frames of success. So I know you can succeed. It's very important that you adopt the same mindset because that itself will contribute to your success. So that's a message, probably the most important thing other than all the content that I cover today, and probably even the content that I cover the entire semester, is to have enough self-belief and enough belief in your own self-worth that even if you struggle through material now, that you do have what it takes to succeed. For example, I'll give you two. When I was in year 10, I took maths and like whatever the math subject was, and I was told, the teacher approached me and said, I wanted to approach you because you're probably going to fail maths. And I just want to let you know that it's okay, you're not a maths person. Some people aren't maths people. And maybe it's just not in you to do maths one day. And you know that it was probably, reflecting on it, probably not the best thing to say to a student. But overall, I think it indicated that if I can fail pretty much year 10 maths and then come here and stand in front of you and do maths in the board in front of a lecture of at least 10% of 500, that you too, even if you're struggling now, can also achieve something similar. Another example, it didn't stop just at stop in high school. It happened in uni as well. I nearly failed a uni subject, and then I came to a professor and said, I'm thinking of not taking your subject anymore. I don't think I have what it takes. And the professor said to me, you know what I look for when I take master's students and PhD students to do research with me? I don't look for the students with the highest grades. Those students are great, and I take some of them as well. But it's important to me because everyone caps out at some point. Your natural intelligence is only going to take you so far. There's only so far you can go along in your career, and your brilliance will just make everything easy. At some point, you're going to run into things that are difficult for you, no matter how smart you are. And what I look for is the students who persist and the students who believe in themselves, even when they're finding that something isn't working for them. And that's the same message I want to pass on to you. That regardless of how you're doing, I hope you'll all do great on the exam. I hope you'll all do great on all the projects. But regardless of how you do, that isn't a reflection of your potential. That's just a reflection of where you are now. And with enough work and belief in yourself, and also wanting to do the thing that you're trying at, you too can achieve whatever success you want to. And so that is probably my most important message of the whole semester. Now, with that said, I do want to turn to our historical figure for this week, and this is Raj Reddy, another ACM Turing Award winner. He was born in India in 1937, and he is an academic staff member, a member of faculty at both Stanford and Carnegie Mellon. Carnegie Mellon's one of the best computer science universities in the world. He won the Turing Award in 1994. He was an early pioneer on AI, and he focused on perceptual intelligence, so machines being able to recognize features and elements of the world around them. So he particularly focused on speech recognition, language, and vision. And now, earlier this week, I think it was just on Tuesday, we saw that OpenAI, the company that makes ChatGPT, released a new version of their product, which now has highly enhanced capabilities in all three of these dimensions, none of which would have been possible without Raj Reddy. Now, one other just fun fact about him, he has spent time in Australia. He has a master's in engineering from UNSW. So we don't normally speak of them, but for today, I'll make an exception for our Turing Award winner. So with that, let's get back to where we were last week. Our motivating question was how to start to deal with very large data. And in fact, this large data will underpin a lot of modern machine learning and AI. So if we don't come up with algorithms to deal with large data sets, we're not going to be able to do any of this computer vision stuff, any of this language stuff. So we were focusing on sorting because that's a problem that we've studied a lot during the semester. And our general strategy to deal with very large data was to divide and conquer, to divide the data up into smaller amounts that we could actually deal with. Remembering that our computer could only fit so much in its memory at any one time, and so we needed to come up with a way to be able to handle those chunks one by one, and then later merge them together. Now, to do this, we needed to learn a bit more C so that we could actually handle files. Now, I'm going to turn back to our example from last class, assuming that's the right button. There we go. And I had some code that attempted to write into some files, but it had some bugs. There are a few bugs here, and I'm wondering if anyone can help me point out some of the bugs. Okay, absent any volunteers. What was your name? Lachlan. Okay, take the microphone. Don't worry, you'll be fine. So what happens if fopen fails?
Returns null.
It returns null, and then what does my program do?
It prints into the error file.
And then what does it do?
Try to read again, or
Say a bit louder.
does it try to read into the?
Yeah, and is that right? If we didn't successfully open the file, what should we do?
Close the file or try again?
So one thing we could do and try again, and if that fails,
Not sure.
Give up is probably the right answer. So we are missing an exit there, and let's do exit failure to be good practice, right? Have I done anything like that anywhere else? Okay, what happens here? I attempt to... What am I trying to do on this line?
Read the
Yep, and what happens if that fails?
nothing.
And so what should I do?
Print an error.
And then,
Try read the next line. Or
if it's not working, the read function's not working, what do we just do
reading.
above?
Stop reading the file.
Yeah, we should probably give up again, exit failure. So this is going to be a pattern that we use for a lot of system functions, is if they fail, print an error and then end the program. For something like malloc, for something like read, if the system isn't doing it, well, that's outside your program's responsibility, and so the right thing to do is just exit. So I had a logic bug here, because I was just ignoring what happened if that failed, which is definitely not the right way of handling it. Okay, so what is my next issue? What happens after I've tried to read for the file? Do I do anything?
You don't do anything with.
I don't do anything. Okay, so that's probably the next issue with my program, that I haven't actually done anything. So let's go to this version that I wrote earlier. And so what I'm going to do is I'm just going to add a loop where I try and read in the data I just read. Okay, and there is one more bug. And this is the contents of, one sec, Isaac. This is the contents of my data.txt that I was trying to read in. Let's run the program and see what happens. And then we'll get to you. Okay, now if I do this, I get a read error, even though the contents of my file look like a series of numbers. Isaac, was that a question or an answer? Okay, so Lachlan, do you want to pass the microphone over? And while he's doing that, I've got a question for you as well. And you can answer my question, and then we'll get to your question. So my question for you is, why did we get a read error, do you think? Let's look at the code briefly. And I tried to read in n ints, was what I was asking for. N ints, and n was 10. And this was my data file.
Can you go back to the read.c code?
Yep. In fact, I can do better, and I'll put them side by side.
I have no idea.
Do I have 10 ints in my data.txt file? How many ints do I have?
Oh, you only have one.
I only have one. It's a really long number, just with the digits 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's try to modify that. And see what happens. Still get a read error. Okay, how big is an int?
8 bytes? 4 bytes?
4 bytes on 32-bit system. And how many bytes do I have in here? This definitely, one way or another, this doesn't look like I've actually written the ints. It looks like I've written ASCII characters, right? I've written the ASCII character for 1, the ASCII character for 2, the ASCII character for 3, along with some ASCII spaces. So in this data file, if I try and read it in, just like the way I would read memory, that's not going to work because I haven't represented it correctly. And you'll see on my tie today, I also have some binary digits to represent that that's some of what's going wrong today and some of what we're going to talk about for the next few lectures. Isaac, you had a question before we get to the solution.
Yeah. Back when we were doing like the exit early,
Yeah?
I think it was in file.io or whatever.
Let me fix that up.
If we exit early, does that mean that we don't free in pointer, which we did malloc before?
Yeah, so that is a good point. It is good practice to, if you exit early, to free everything. However, as part of the cleanup for your program, when the program exits, the operating system does reclaim all the memory. So you're not going to cause a problem for the most part if you just exit.
Is that just if like you exit early? Like it frees everything if you exit failure.
Yeah. So exiting will instruct the operating system to release all the memory under ordinary conditions. There are some exceptional conditions, but we don't have to talk about them. Okay, so we've recognized our problem is that we have tried to read in integers from a file that's really ASCII. So let's take a look at our write function, our write program, which I prepared earlier. And here I've done the same kind of thing. I put out these numbers into an integer array, and now I'm going to use very, very, very similar code to write them out to the file. So instead of, let me change these to exit failure just to be a good programmer. And instead of read, I'm doing write. Now you'll notice the other thing that I've done here is I have used the W flag to indicate that I'm writing to the file, and also the B flag to indicate that this is not ASCII, this is binary. Because what I want to do is I want to make sure that I don't treat line endings like a /n as a /n. I just want to treat it as another byte. So I want to treat the whole file as if it's just a sequence of bytes, and then I'll read them in as integers. So, or write them in as integers. So let's compile write, and then I'll run my code. Done, and then I'll run my read program again, and now I can see that it's successfully printed out the numbers. So what I'm going to do now is I'll try and open this write file. If I open data.txt in the text editor, let me find the right one, bcd data.txt. We get this weird looking stuff. When I try and open it in my text editor, it doesn't work. And that's because this isn't ASCII, so it doesn't display in a text editor normally, it's just a sequence of bytes. And Visual Studio Code doesn't know that it's meant to be displaying those as if they were numbers by interpreting them 4 bytes at a time. Visual Studio Code just expects ASCII characters, and so it doesn't display it properly. Now there are programs on the computer that will try and display it properly, and you can give them flags to tell them how they should interpret a file. So let's use one called XXD, which is standard on many Linux and Unix machines. And now let's run it on data.txt. And now we can see the actual bytes inside the file. So we can see these are the addresses within the file. So starting at location 00, I have 1 and then 3 bytes that are 0 because it's a 4-byte integer. And then I have a 2 and another 3 bytes that are zeros because that's the number 2 in our integer representation in memory, and so on and so forth. And let's see if I can remember. I think it's the G flag. Yeah, it tells me to display it in groups of 4. So now I can actually display the entire integer as they are represented in memory. If these were 64-bit integers, then I would have to do -G8 to display 8 bytes at once. And so now we're starting to get into the weeds of knowing that we have to figure out ahead of time how we're representing data in our file if we want to read it in successfully. And just one more note on this. You'll notice in my read, I've also used the B flag there in the reading to make sure that it treats bytes the same way. Now, if I wanted to write in ASCII characters, I wouldn't use this B flag because I wouldn't need it, because I'm just going to be writing ordinary letters. However, then, when I'm doing my fread, instead of size of int and an in pointer, I'd need to change this all to characters, and then it probably would work out. So any questions on that before we move on a little? Finn, let's pass the microphone to Finn. Oh, yeah, go for it. Finn will get to you.
Is this on? Oh, yeah. With the... Is there a way to read, I guess if there's ASCII values in a file that say 1, 2, 3, 4, is there a way to read those and convert it to their actual integer? Because like the...
So how would you do that? Let's say you open a file, it's got ASCII characters.
Because like the integer value that they would correspond to would be like the ASCII value that prints those out.
So have you seen a function anywhere this semester that allows you to convert ASCII strings of numbers into the underlying number?
You get the difference between the two.
So you could do the calculation yourself. Have you seen a built-in function that does that?
No.
No, it's one of the exercises, but I will give it to you. There's a function called a toy. And if we look this up, converts the initial portion of the string pointed to by string to its integer representation. So you can do it yourself. This function, you do have the skills to write this function yourself if you wanted to, but there's also a built-in library function to do it. Okay, let's pass it over to Finn.
My first question actually is it pronounced a toy? Is that how you say it?
That's how I say it. I don't know what the official pronunciation is.
I imagined it was like alpha to integer, so I always thought it's A to I in my head, but
That makes more sense.
a toy sounds cool though. That wasn't my question. My question was,
You've used up your question points now. No more questions.
I didn't quite catch why there are so many zeros after the numbers again. I didn't quite.
So a 32-bit integer has to be able to represent anything between negative 2 to the 31 minus 1 and 2 to the 31 minus 1, like the positive and negatives, right? And to store numbers in that range, we need 4 bytes. If we were storing the number 1 as 1 byte and the number 2 to the 31 as 4 bytes, then we'd never know how many bytes to read in at once. So instead what we do is we say for any integer, always use all those bytes, and then those bytes will always represent a number in that range.
So I get that, like in terms of the binary representation, that's what it would be doing. But when it prints it out, it's in hexadecimal, it looks like, I think, because it has an A there. Or is that not the case?
I think, yeah, these are in hex representation.
So the extra zeros are like,
They're another byte's worth. Remember, a 2-digit hex, a 2-digit or 2-character hex representation ranges between 00 and FF, which is between 0 and 256. You do that 4 times, that's 4 bytes.
okay. And why is it aligned to the left like that and trailed by so many zeros? It's like in binary, if you start at 1, it's like the bit on the very right is...
So that is a detail that is not important for our class, but different architectures use either the most significant bits or the least significant bits as the place that they start from. So on this computer, that's called endianness. We're going from the big end to the small end, and in other computers you go from the small end to the big end. And that's just an implementation detail about the way the circuitry has been designed.
Okay, thanks.
And you'll see that maybe in your 3rd year class, computer systems. Okay, so we now have all the tools we need to do a technique to sort across a whole bunch of different files. There are also other functions to seek to locations in the file according to the address in the file, but you can look those up on your own time. So our idea now is we want to split up our work so that half the items that we want to sort are going to fit in each chunk. And this leads to our algorithm called Mergesort. So now I want everyone who's been selected to hold a card to come out down to the front. Sebastian, you've got Finn had the big brain. Sebastian, you've got a card. So hurry up and come down so we don't spend too much time of lecture. And there are cards at the front for you to pick up.
It's
Got
hard
it?
to turn because there's so much weight on my head right now, but okay. Okay.
Okay, take a bow.
No.
Okay, so we are going to learn to do Mergesort. Now, do you already know Mergesort?
Conceptually, kind
Okay,
of.
so you've cheated a bit. So this is going to be a little easier than it could have been, but...
Pretend I don't.
So our very first step that we talked about was we said we had too much data to fit in our computer's memory. Now let's say we have room for 4 items at a time. So what would be our first step with...
So I think we're gonna... Are we just gonna split them down the middle?
Yep, okay, split down the middle. You guys go off to this side. You're out of the computer's memory. Go off, go off, go off. All the way. You're hidden in the corner and no one's ever going to see you again. You've been deleted. Okay, great.
Okay. Now, can you show me...
Wait. I think we can still do another split. Three's too many. We don't have a computer instruction that allows us to compare 3 things at the same time, do we?
Oh, yeah, that's true.
Okay, so Cassie? Yeah, but don't go all the way as far as them. They're from the other. Yeah, that's pretty good. Okay, so now what do we do? Do you know how to sort a 2-element array?
I think so.
Okay, so let's try. Now remember that we have our audience over here.
Okay. Can I see your card, please?
And let's get names from everyone.
So, what was your name? Tristan. Okay. Got it. It's an A. So, are we ordering? So, ace is high.
Yeah, let's do ace low.
Ace low. Okay. You can turn that back around then. And what's your name? Gabriel. Okay. Can I see your card, please?
And we can remember we have room for 3 things in our memory at once. So Tristan, you can keep yours turned around.
Oh, cool. Okay.
And let's go from, let's have the largest item should be on that side.
In that case, we need a swap.
Okay? Have we sorted our 2-element array?
Yes, this
Okay.
is sorted.
So let's close those back. Are we done? Have we sorted all our elements?
No, we've got all those guys over there.
Okay, so I guess Cassie, you're next on the list to come back. But remember, we can only compare 2 elements at once. So who are we going to compare?
I want to compare, I guess, the leftmost one, which is Gabriel, right? Yes, and then Cassie, was it? I want to compare those, I think.
So we can try it that way.
And this is okay. So now I need to check with Tristan and Cassie, I think. And now we need to swap them. Okay. And this is sorted. Do I have to verify it again, or can I
Okay,
just...
so let's flip them round.
Okay.
Because we know that if we've put Cassie in the right spot relative to that one, then we should be okay. So let's flip them back around and close them up.
Okay. Now do we bring one more person over? Or do we... No, we do the same thing over there.
Okay, yeah, let's do the same thing over here. That's a really good idea. So all of you 3, step forward over here. Now this seems difficult because again we've got too many people to compare. So what are we going to do?
What's your name? Okay. Can you go stand over there, please?
No, Toby, you're being exiled.
Sorry, Toby. Okay. Can I... What's your name? Nabia. Can I see your card, please? 4. Okay. What's your name? Sebastian. Okay. Can I see your card, please? We need a swap. So, swap. Okay. This is sorted. Now, can I bring Toby over now?
Okay. We've got a sorted array, so close yourselves up.
Okay. Can I see your card, please? Okay. Can I see... Navia, can I see your card?
Wait. Why are you suddenly so... With the other one, you were starting from the big end.
I think that was a bad idea.
Okay, bad idea. Okay, so let's forget what we did before, and instead let's start with the small end when we try and add one along.
Wait, actually, it doesn't matter which one I start with.
As long as you're consistent.
Well, okay, I haven't been, but this is the new convention. Okay.
Okay, this is the new way we're doing it. From now on, we're going to check the small end of our subarrays first.
Okay, can you guys swap? Okay, then you can turn your card around so I can see Sebastian's card because I forgot what it was. Okay, this is sorted. Now I need to combine them.
Okay, so this is the bit where it's actually going to get tricky. Sebastian, turn your card around again. This is the bit that we've been struggling with so far, is figuring out the combining. So we know that our basic strategy is going to be keep splitting recursively, then sort the subarrays and try and merge them back together. And this is why it's called Mergesort. So let's try a strategy where let's look at one end first. So let's look at the small ends of both of them first.
Hang on.
How does that sound to you?
Can you hold this microphone so I can swap hands?
Okay, there we go.
Thank you. I was getting tired.
Okay, so let's try look at the small ends of both our subarrays first.
The small ends.
Who do we turn around? Do you remember your names?
Nabia,
Good job.
can I see your card? Okay, 4. And then I go over here, I think.
Yep.
Tristan, was it?
Good job.
Ace, okay. This is smaller, so we're going to swap it over there, I think.
So instead of doing swapping, let's assume that we have enough hard drive space to store these in files, and let's just bring the one we want forward. So which one do we want first?
What do you mean by first? Like,
Let's say on the left, on the small side.
wait, you said on the left on the small side, but the small side.
It depends who's left and right. Small side, big side.
Okay.
So who's smaller?
Nabia.
No,
Wait, no, sorry.
Ace,
No.
ace low.
Ace low. Okay. Tristan is then.
Okay, so Tristan, go out in the very front, and you will be the first element in our final array.
So he's somewhere else in memory.
Yeah, he's somewhere else in memory, just in our final layout. We've copied him.
Okay.
I'll have to do some fancy visual effects to ensure that a copy stays there as well.
Okay. Next then, I'm going
Can
to...
we just copy Nabia over? Do we know that she's next in
No,
line?
we don't know that because I need to check Cassie's card first.
Yeah, so we aren't sure that Nabia should be next because it's possible that Cassie is next in line. And in fact, that actually turns out to be the case.
Okay.
So
And
now do we know who should go there?
yes, I think so. So you can go stand to the right from the camera's perspective, I think.
Yeah, on the bigger side of Tristan.
Yes, that one.
That's good.
Okay. Now then, I need to see your card, please. And it is smaller than that, so I think you also... Yep, go join them. And now I can just put them all...
Yep, put them all one at a time. Nabia, up you come.
That's right.
Toby, and then lucky last Sebastian. Okay, let's rewind to our subarrays for a second. So that's great, we're sorted. Let's rewind to exactly the positions you were in 2 groups of 3. Come on, rewind. Vroom. And we're going to do one swap just to see what happens. So the way you were before, on 2 sides of the room, in the same order. So was that the sorted order, in the sorted order in the subarrays? So Nabia, you were the smallest. And let's switch. So turn them around just so I can see this. And we're going to switch one to just see what the algorithm would have looked like had they been arranged a little differently. So now I'm going to take this, and we will give that to, we'll give it to Gabriel. And now we're going to have to do a change here because that will have to be there. So that's still sorted. Okay, so now let's do our process once more. Turn them around, and we'll do our merge with a slightly different ordering. Okay, go for it, Finn.
I need to see your card. Okay. So I'm sorting the subarrays first.
Subarrays
right?
are already sorted.
Oh, they're already sorted.
We're
okay.
doing the merge step.
Okay. And then I'll compare that, I guess, to Nabia's card. Okay. So in this case, I want to put Tristan there first.
Yep, Tristan's still there first. He's still the smallest element.
Now then, I need to see Cassie's card, which is also smaller than Nabia's, so you can also go join the final array. Then now I need to see Gabriel, wasn't it? And you are much larger than 3. So Nabia can go to the final array. Now then, Toby, I need to see your card. That's smaller than the jack, so you can go to the final array. And then, Sebastian, you have a king, don't you? So you stay there, and then you can go to the final array. And now you can go to the array. And it should be sorted.
And now you're done. That's our entire merge sort. Can we have a huge round of applause for Finn? Okay, everyone can put their cards back, and we'll take the big brain. And thank you very much, Finn.
Big brain is not what it was cracked up to be.
Now, big brain needs some repairs. If anyone's very good at DIY. And this is just showing essentially the same process. We're going to keep splitting things into subarrays. We're going to sort the subarrays. And then we're going to merge them back together. And the way we merge them back together is by looking at the smallest element in each of them, or the largest element if we're doing sorting the other way, figuring out which one to put first, and then doing that repeatedly, looking at the next element along with the other one that we didn't put in, and do it over and over and over. I'll let it play out. But this is exactly the same process that Finn went through. So Finn, if you had to say this out loud in pseudocode, I'll give you this one more time. So let's do a recursive version.
Okay. So just start talking through it.
Give me a second. I will write up your pseudocode in a notepad.
Okay. So I want to split the array down the middle, which is, I guess, how do I say that in pseudocode? Split it. Is that fine? Or
Well, let's
I
just do
guess-
split. And then how do we split? Someone quickly tell me. Yeah, so if we have n split index equals n divided by 2.
yeah, that'll work. Okay. And so then I'm gonna, I guess if we do it recursively, it'd be
Yeah.
calling merge sort on that first half, and then on that second half. Okay.
And then do it on the other half, you said?
Yeah, that's right.
Oh. And then what do we do?
So do I need to handle the base case, I guess?
So we do need a base case. Good point.
So I guess if there's only one item, then it's already sorted.
And so we
I
should
haven't-
pass in n to each of these.
I haven't done the merging, and I'm not sure how that's gonna look.
That's okay. Let's just call it the merge function. So we'll do the merge on, and I'll copy this. We want to merge the left half with the right half. And that will do for the time being. We won't make you sketch out the merge code as well. So that is essentially our entire merge sort. And I can also represent it that way. Now you'll notice here I've been a little iffy with my n. I haven't said that n is actually passed along like I did in my other pseudocode, but just for argument's sake, say that the value of n is updated in the next, when you pass the array along. You can always calculate the array's length. Now what we get to is the merge function. Whoa. Get to the merge function. And the merge function, essentially what it does is it uses pointers to keep track of which item it's looking at in both halves of the array. So remember that we were looking at Nabia in this half, and then we were choosing who in the other half we were looking at the current time, depending on who we'd already placed forward. And that's essentially all we're going to do here with our S1 and S2 pointers. S1 will be a pointer that points to, say, the left half, and S2 will be a pointer that points somewhere in the right half. And as we go along, we'll choose which of the two elements is the one that we want to put forward into our final array, and then move that pointer along by one. If it's the element that we're not putting forward, then we just leave the pointer there. So we don't move both pointers at the same time. What we're doing is choosing which of the pointers to advance based on which of the elements we decided to put forward. So if we put forward something from the right half, then we move the right pointer along one because we need to look at the next element. If we have selected something from the left half to be our next element, then we'll move the left pointer over by one. And although it seems a little intimidating here, if you go and actually work this out by yourself, you'll see it's actually very, very similar to the process we just did with Fin. There's no material difference. So let's look at the way it's actually implemented in C code. So here is something I prepared earlier. So here we have our merge function, which is pretty much identical to both the pseudocode and to what Fin did. So start with the index that how many items you have put into the final array. Have a pointer to the left half and a pointer to the right half. And what we're going to do is we're going to successively copy sections. So the first thing we have to do is we have to set this up, copy the first section into the temporary array. Then what we're going to do is we're going to merge the second section into the array based on the procedure we just looked at. And then finally, if we're at the stage where, remember how we'd gotten to this point where we'd finished looking at all the elements in one half, but we still had a bunch of elements from the other half left, this is just going to be copy the remainder that's left if the other pointer has already passed the end of that half that we're finished looking at. Mergesort is exceedingly simple itself, just like quicksort, so the details for a lot of our sorting algorithms are not in their high-level structure, but either in the partition function or in the merge function. And for those of you who are worried, this code is available after the fact on the course website via links in the slide packs. So let's give it a run. And let's compare that to quicksort. Ooh. Need to compile it for this computer. There we go. So we can see that actually on this small set, on the particular set that we've done, Mergesort has actually ended up being more efficient than quicksort, which is surprising given that we've talked the whole semester about quicksort actually being the quickest one that we actually use in practice. But there's a small caveat to that. On small arrays, Mergesort often ends up empirically being better. And so what real implementations use, so if you use qsort in the standard library that we talked about, what it's often doing is some mixture of Mergesort and quicksort depending on what the array looks like at the beginning. And so it will choose for maybe a very small array to do Mergesort and for a large array to do quicksort. And then this is going to depend on what you know about your array going in, which of the sorting algorithms do you want to use. If it's really, really big and it's not going to be able to fit in memory, quicksort's going to be the wrong approach. Mergesort will be better because then you can split it up into files. If you know that you want the best worst case guarantee, then you'll use heapsort because heapsort has that guarantee. If you just want a generic sorting algorithm that's going to perform pretty well overall, then you might use quicksort or even better qsort, which does this kind of like mix between all the different sorts. So as with everything else this semester, we now need to do our formal analysis of Mergesort. So this turns out not to be too complicated. Here we have the recurrence relationship, which is a merge of n steps, because remember our merge, we only ended up looking at every element in the whole thing once for each level, plus we have to do 2 times the amount of work that it was, however much it was to run Mergesort on the subarray. So this term here is accounting for the fact that we do Mergesort on the subarray, and we have to do that twice, because we have 2 subarrays because we've split it into 2. How large does the merge back together take? Well, it takes as many items as there were on that level. So, like any other recurrence relation, we're going to need to solve this, and the details of that will be left mostly to next year for you. But let's try and do it a little bit. So if we expand this out and actually figure out how many steps it takes for us to do when there's only one element, well, it only takes one step. What about when there are two elements? Well, that is 2 times 1 plus 2, because that is our 2 subarrays, each of which took 1 step, plus the additional 2 steps, because on that level we have 2 items to look through for the merge. So let's grind this out, let's write it as a series and figure out how to represent a new variable that will create k in terms of the number of elements of the array. So let's set log n equals k. This is a usual step, we've done this a few times before. If we solve the recurrence relation and write out all the terms, we know that there are k terms, so there are log n terms. And so what we have to do is we have to do log n multiplied by the largest value in that set, which is, if we do the summation properly, we get n plus n on 2 log n. Out of these, n log n is the largest term, and so we get O of n log n worst case. So a challenge for all of you is the merge sort that we've done relies on having this additional array at the front of the class or somewhere else in our computer's memory that we use as extra temporary storage to store things into. Now that could be a file, it could be our system memory, but there is actually a way of writing merge sort without an extra array while still preserving the n log n runtime. So it's not so easy to code up, but if you want to give it a try, come up with some ideas and then check out the implementation on Wikipedia. So what is the wisdom from all of this? How can you remember what merge sort does and what quicksort does if you're in an exam situation? This is the wisdom of Alistair Moffat from your textbook and from the other semester, which is that quicksort is hard split. So where our partition is difficult because we have to figure out which element goes in the middle partition and the left partition or the right partition, but then joining them is super easy because everything's already in the right order. Merge sort, we have an easy split. It's just split them in 2, but then the joining process is hard because then we have to do that thing where we have our 2 pointers and we figure out which one comes forward. So this is patented Moffat wisdom. But now doing it with files is where some of the complexity comes in and where your implementation skills will really be tested. So now we're getting to near the end of semester, so we can start introducing a little bit more unassessed material, which is just for your edification and potential enjoyment. So can we use a priority queue to make humongous sort faster? So assuming that we have a lot of data, can we actually start to use some of our other data structures to make things even better for us? So a naive version of this, using a priority queue, is put all your elements into the priority queue and then pull them out one by one. And we had a name for an algorithm that looked very similar to this. What was it? Heap sort. Heap sort looked very, very similar to this. So essentially, a heap can be a form of a priority queue, and what we were doing was we were pulling those elements out one by one by one. So that's the naive version. And we know that that gave us worst case n log n time. So there is this beautiful paper from Wei and Yi, 2014, so not that long ago. This is still like kind of current research. And this talked about this beautiful equivalence between the way a priority queue works and sorting. And you're not expected to be at this level of research yet. It's just to kind of show you that this is still an active area of discussion. So they said, start with a sorting algorithm that sorts n keys in n times s of n times. So you can imagine s of n time might be log n, it could be some other function. That implies, mathematically, that there's a priority queue that uses the sorting algorithm and then has insertion and deletion in big O of s of n time and find min in constant time. So this says that there's this deep algorithmic relationship between these two types of operations, between having a priority queue with insert, delete, and find min, and with sorting algorithms. So that takes us part of the way there. But a humongous priority queue also isn't going to fit in memory, so this kind of doesn't work super well. So how do we then go from this kind of interesting structure to being able to deal with humongous sort? So this is external merge sort, and external merge sort is the way we used to describe it with files or different computers. And you can also do this with a priority queue. So then you split the data into chunks, you sort each chunk, and then merge the data using a priority queue. So you can use a priority queue just for the merge, so you can do this fairly well. So here is I haven't said what year this is, but I think this was like 2018. This paper says, we designed a priority queue that uses the sorting algorithm as a black box, such that the cost of insertion or deletion is the same as the cost of the sorting algorithm. So again, this super deep connection. And you end up getting this algorithmic complexity at the end. You get O of k n log n time and O of k n space for k splits each of size n. So the n here is only a subset of the total data. So let's say our total data was m, and we split it k ways. That means that n will be m on k. So we've split it into k chunks. It's a little tricky to say. Now, we're not totally done with sorting. Now, while you can prove that O of n log n is the worst case for normal sorting, we're not always doing normal sorting. I keep emphasizing that the best algorithm for you is going to depend on the data that you have coming in. So we have a bunch of different sorting algorithms that rely on special cases where we know something more concrete about the data. Toby was actually asking me about this at the end of class the other day. He said, I've got a friend who's come up with a sorting algorithm that's better than n log n, but it relies on the fact that you know something about the data coming in. So in this case, it was that all the data is part of a set of consecutive numbers. So that was what Toby was bringing up. So if you know that there is a finite space in which your keys fit in, so you know all the keys are between 0 and 100, for example, there's an algorithm that's O of n times log n, and log n is much smaller than log n. And then that only uses O of n space. There's also a randomized integers sorting algorithm that takes O of n root of log n expected time. And so there are a whole variety of these like special case sorting algorithms if you know a little bit more about the data. So this is also a really fun thing to bring up and surprise a technical interviewer if an interviewer is asking you about the best sorting algorithm. So that concludes our entire semester's discussion of sorting. You're now sorting experts. And hopefully the next time I teach this class, I'll see your name when I go to Wikipedia and look up some of these special case sorting algorithms. It could be, I don't know, Finn's algorithm, a randomized algorithm for sorting students in a class or something like that. Okay, so with that, let's take a few minutes break and we'll resume at 2:53. And we are back. And we have a new motivating question for some of today. And this is, how many degrees of separation are there between you and the current King of Australia? Yes, I know it may be anachronistic, but Australia still has a king. And what do I mean by degrees of separation? This means how many people do you have to get through, how many friends of friends of friends of friends of friends until you get to the king. So for example, if I want to get to Kevin Bacon, who's a famous actor, I might have a friend who's been in a movie with someone else, with Angelina Jolie, and Angelina Jolie has been in a movie with Kevin Bacon, so I count the number of hops I have to get. So I have to go to one friend, that one friend to Angelina Jolie, and then Angelina Jolie to Kevin Bacon, that's 3. And for actors, we call this their Kevin Bacon number. So it's how many, if you've been in a movie, how many co-stars do you have to jump to get to a movie, to get to Kevin Bacon? So if my co-star has started a movie with another co-star who starred with Kevin Bacon, that's 1, 2, 3 hops. And we call that your Bacon number. Now, mathematicians maybe don't watch as many movies, and so we also have something called your Erdos number. And there was a very famous mathematician called Paul Erdos, and he was prolific. He published papers with tons and tons of people. And so mathematicians instead have an Erdos number, which is how many co-author jumps do you have to do until you get to someone who's co-authored with Paul Erdos, and then you do one more jump, and then you get to Erdos himself. So for example, my Erdos number is 4 because I published with someone who published with someone who published with Paul Erdos. Now, if you are very special and you are Natalie Portman, does anyone know a bit about Natalie Portman and what might be interesting about her? Give me a couple Natalie Portman facts. Sebastian.
I think she has done some research.
She has done some research in what field?
Something, science, I can't remember.
Something kind of STEMmy. And what's the other thing that we should know about Natalie Portman if we live under a rock? She's an actress. What movie did she famously appear in?
She has
Come on, the big one.
like Star Wars.
Star Wars, okay. So Natalie Portman is a published research author and is in Star Wars. So Natalie Portman is in possession of what we call a Bacon Erdos number, which is the sum of your Bacon number and your Erdos number. So my blessing for you is that I hope you aspire to have the lowest possible Bacon Erdos number. So I hope you appear in a movie, and I hope you publish a research paper, and that these are both very close together. Unfortunately, I do not yet have a Bacon Erdos number, but maybe after doing enough of these lecture videos, I'll be invited to be in some film as well. So let's get back to our question after that. Actually, before we get back to that, we've got enough time. I will tell you one or two fun anecdotes about Paul Erdos. So Paul Erdos had a somewhat challenging life, and after the death of his wife, he abandoned having a home. So for the remainder of his life, I think he was like 45 at the time, he sold his house and never had a house or a place that he rented for the rest of his life. Instead, the way he produced so many papers is he would travel to universities, meet with a co-author, sleep on their couch for a few days, work on something together, and then move to the next person. And that is how he became so prolific. He was also very, very smart. Now, on top of that, he also had an amphetamines addiction. But he claimed that this is what helped him be very, very productive. And I tell this to my PhD students when I tell them they're not allowed to use drugs during their PhD as performance enhancers, or generally as well. But Paul Erdos was addicted to amphetamines, and he had a bet with a friend came up to him and said, you know, Paul, this is really not doing you any good. You should cut out the amphetamines. You've got an addiction. He says, no, I don't have an addiction. I could quit at any time. And we've heard that one before. And the friend said to him, fine, I'll make you a bet. Get off amphetamines for a month and we'll claim that you're not addicted. So Erdos went away. A month passes. He comes back to his friend, and his friend says, well, did you make it? Paul says, yes, of course I made it, but you set American mathematics back one entire month. So take that as you will. That is not an endorsement of amphetamine addictions. Anyway, those are my two fun Paul Erdos stories. So how many degrees of separation between you and the king? Does anyone have a guess for their personal king number? Toby?
Less than 6.
Less than 6. That's pretty good. Anyone else have a guess at your personal king number?
Probably a
Surprisingly low. Maya, what's your king number? No? Take a guess. Isaac? 1, you know the king? You are the king? Okay, so I will let all of you know now that it is probably pretty small, and in fact, I will give you one concrete upper bound on your king number. Okay, so how can we check? Let's say that we create a graph, which is kind of like a tree, just with more edges and more connections, that links everyone that you're friends with. So here we have a potential set of links between people in our class who know each other. Now, I know you've been sitting very far apart, which is why some people aren't linked to other people. So this is a tree version, where everyone has maximum of 2 friends. But I know at least some of you have more than 2 friends. Toby, do you have more than 2 friends? Yes? Finn? Finn's not sure. You've got at least 1.
Okay, yeah, I think that makes it.
That's 2 then?
That makes it 3.
3. Okay, who are the other 2?
You don't know.
Oh, okay, so I'm not connected to them. Well, given that Finn's got 3 and Toby's got more than 2, we're going to need a better structure to represent this. And it's also the case that most people's friendships are reciprocal. Now, Sarah, I don't know if you consider me a close friend, but I've always I've always been fond for you. So hopefully we have a two-way arrow between us as well. And so we need to adapt our tree structure a little. So this is already getting to be a little different. And now let's add in all these other links to everyone else. So our structure of just having a left child and a right child is now no longer enough to represent our data. So we might start needing to have arrays of pointers or some other structure that we can use to represent the links between everyone. So you'll see that Shadman over there has a very special friend. Not friends with anyone else, but some among us are spies. But let's take away all the arrows just for convenience sake. But really, there's a single answer to who is the most popular in this class. Does anyone know? Who has the most friends? Finn's got it right. Whoa. Let me put that back. So, of course, I'm overjoyed to have the most links, but there are a few more personal facts that you should know about me. I have a high school friend whose name is Maddie. She's given me permission to use her in this. And she met Prince Harry, and Prince Harry met the king. And so let's see where did the embarrassing pictures not come up? Hopefully they'll be somewhere in there, but I have some nice embarrassing, I think it's here. Here we go. There we go, nice embarrassing photos. So that is me in, I think, year 9. And that is Maddie with Prince Harry and Prince Harry with the king. So you can see this all works out. So let's go from, Jerry, you here today? No, Jerry. Angela's not here. Jai, you're here. So Jai, we can go from Jai to Andy. Is Andy here? Wow, class is empty today. Okay, Jai is friends with me, so that's one link. I'm friends with Maddie. Maddie is friends with Harry. Harry is friends with the king. You've got, all of you have a maximum king number of 4. So that's pretty cool. But we have to find a way to calculate this. I mean, we can obviously do it if you see the whole picture at once. But one of the things we've been struggling with our sorting algorithms is that the computer doesn't look at the whole picture at once. It just looks at like 2 elements and compares them. So we need to algorithmically get the number of degrees of separation. We're going to need something a little better. So let's start with these preliminaries. We're going to call each person a vertex V. It's like a node, except in the terminology of graphs, which is this data structure we're talking about now, we're going to call them vertices instead of nodes pretty frequently. And we'll call a link an edge. And so the set of vertices will be V, and the set of edges will be E. So we have a couple of different strategies that we could use to try and find out how to get from a given person to the king. So our first strategy could be to go deep in the graph. And so let's start at Angela. And from Angela, we'll look at all of Angela's possible connections. And then let's pick one of those connections to start with. We'll go with Jai. And from her, we'll look at all of her connections. And then we'll look at Asan and all of Asan's connections. And then we'll go to Shadman and all of Shadman's connections. And there's a dead end at James Bond. And then we'll try all of Dr. Connie and all of Dr. Connie's connections. And then we'll go to Maddie. Maddie only has one connection to Prince Harry. Prince Harry only has one connection to the king. And so this required us to travel through 7 steps to get to the king. It got us there in 7 steps, not quite the shortest path. So this did help us explore the graph. It was one strategy to explore it, but it didn't quite work. Okay, let's try something different. So we will go broad. Let's try this now. So let's start with Angela. And then we will put Jai, Andy, and Dr. Connie up next. And we'll look at each of them first. Once we've looked at each of them, we will look at each of their connections. So we see Asan, Evelyn, Jerry, and high school friend Maddie are all 2 steps away. So the blue lines are all 1 step away. Now the pink lines are 2 steps away. Now everything in yellow is 3 steps away. Now, everything else would be 4 steps away. So now we only travel through 4 edges. And by looking at it either by going deep or going broad, you get these different properties of either finding out what's at each level away or being able to go really deep really fast. And these are known as depth first search for the deep and breadth first search, going broad, going far in each step. And these are 2 different types of search algorithms that you can use on graphs to find a given element. So the idea for this one was to put each vertex in a queue instead of a stack, and then repeatedly remove the top item. Yes, Jack?
Are these at all similar to Dijkstra's algorithm?
Dijkstra.
Oh, is that how you say it?
Yeah. Dijkstra, which is, so it is not on you for failing to pronounce that at all. It's a tricky name. So Dijkstra's algorithm is a path-finding algorithm similar to this, only it works when each of the edges have a different length. So assuming you start caring about the length of the edges, Dijkstra's algorithm will help you find the shortest path. But yeah, Dijkstra's algorithm is very closely related to breadth first search. So let me say that one more time. So for depth first search, the way we do it is by putting all our nodes on as we encounter, all our vertices as we encounter them in a stack and repeatedly remove the top item. And for breadth first search, we do the same thing, just with a queue. And this again indicates some of the deep links we're getting between our data structures. So we've got links between our algorithms on our data structures and also relationships between data structures and other data structures. We have gone, just like we went from trees to binary search trees, we can also do a similar thing where we went from linked lists to binary trees, which are a little more complicated. So linked lists just have 1 link. Binary trees just have 2 links, and they always represent children. And then we can go to graphs, which have even more links. So each of these is a path going along from most restrictive to less restrictive in terms of the number of links that a given node has. So how do we actually put these into a C program? Well, the first thing you might think of doing is like this. We expand our type def for a node, and we have link 1, link 2, link 3, link 4, link 5. What's the problem? Link 6, link 7, link 8, link 9, link 10. When do I stop? Tristan? Yeah, you don't know when to stop. What's the maximum number of friends a person can have? Well, actually, that's probably not the best example because there is a reasonable limit on the number of friends a person can have. It's called Dunbar's number. But realistically, from writing a program, this isn't a particularly great idea because we'd have to write like one of these lines for every possible. This is the wrong idea. Okay, this is a better way of doing it. What we can instead do is we can have an array of nodes that can contain multiple nodes, and we'll malloc this and we'll use it to store as many nodes as we want. Or we could have a linked list of nodes. So now we have our linked list of edges over here, and we can store all the links that a given person has in a linked list. So we use a linked list as part of our representation of the graph. So any given node has within it a linked list to all the other nodes that it's connected to. So that's one way of doing it. So then we would have 12, for example, in our graph from before, we would have 12 different nodes, each of which is attached to their own linked list. So this is what it would look like. Angela is connected to, let's do Jai. Jai has seemingly the most friends out of everyone next to me. And so she has a linked list of her friends, and she has a link to Angela, a link to Andy, a link to Evelyn, a link to Asan, a link to Shadman, and then a link to me. And all of these are in her linked list. So everyone's got their linked list. But there might be another way to represent this other than linked lists. Oh, that picture is from last year. But this is looking oddly like some other kind of data structure now. What does this look like to all of you? This look like linked lists? What does it look like? It looks like a table. What do we call a table in C? It looks like an array. looks like a 2D array. So we've got an array where on one axis is all the different people, and on the other axis, well, it doesn't quite work yet, because each one of those cells represents something different. So we might have to do some rearranging. One other thing to note is that every edge here is appearing twice because our edges are double-sided. So you'll notice that number 9, Connie, has a link to Jai, number 1, and Jai, number 1, also has a link to Dr. Connie, and number 9 over there. So we're also doing some doubling up over here. But if we were to calculate the runtime of both of our search algorithms, we would find that they have a runtime of the number of nodes plus the number of edges in the graph, worst case, because worst case you'll have to go through all the links and all the nodes in order to find something at the end. The simplest way to imagine that is imagine everyone only has 2 friends to get, and those friends are all like in a line, so I'm connected to Finn, and Finn is connected to Zelfin, and Zelfin's connected to Hamish, and so each time you can only have one possible hop to go to, and if we do that for everyone in the class, then we'll have to go through every node and every edge. And this also has a space complexity. These algorithms also have a space complexity of the number of nodes that there are in total. So as we said, this looks like a big matrix, but it wasn't quite in the format we needed. So if we do a little bit of tweaking, we'll get something that looks a bit more like this. And so now our rows and our columns look the same, and I have the names of all the people in the rows and the names of people in the columns. So let's go Dr. Connie and Jai. There's a 1 in there. True, we are friends. And if we go to Jai and Jai, like row 1, column 1, there's a 0 because she's not friends with herself. Have you been treating yourself okay? Okay, she has. So you can choose, depending on what kind of program you're representing, to either have a link to yourself or not, but in this case we don't. But you can see that Jai at number 1 does have a link to Dr. Connie in the Dr. Connie column. And so we have another way of representing our graph in a program by a matrix. And now, of course, we probably want to fill it out properly with the zeros for the things that aren't true. Only now, when we run these algorithms, we've got an O of the number of vertices squared. So that's not quite as helpful. So now we can also do a check quite easily to see who people are friends with. So we can scan, for example, along their row and see all the different people that they're friends with. So let's try going one way to see who Angela's friends are. So we can go down the Angela column and we hit our first ones. That's Jai and Andy. And so we see they're both friends. We can also look at the overlap between any 2 people's friends quite easily. The way we do this is by, say, highlighting 2 rows at once and looking for places in which there's a 1 in both rows. Now, this is something we couldn't have done in our linked list representation, even though our linked list representation ended up being more efficient. So again, we've kind of got this message that's coming through over and over in the class, which is that depending on the particular things you want to do with your data, a different representation of even the same abstract data structure is going to change what's more efficient for you. And we saw this with our queues and our heaps, that different ways of storing the underlying data would result in different properties. So a challenge for you to maybe think about at home is how to do this overlap thing with adjacency lists with that first linked list style structure, if it would be possible. What do we tend to do in reality? Mostly, we do tend to use that linked list representation, but we might use the matrix representation for a number of different cases. And again, have a think about what are some cases that you might use that for, because a potential assessment question is, okay, here is a scenario. Which of the 2 concrete representations would you use in this scenario, given what you know about the algorithms? So what about implementations of all the graph algorithms? Well, for that, you're going to have to wait for next semester. So now we will take a few more minutes and I'll just give you an intro to tomorrow's class and then we'll wrap up. And we'll probably repeat a bit of this intro tomorrow. It's just to give you a flavor. So at this point, all of you know I'm a bit of a Swiftie And so we do have our final Taylor Swift themed lecture for the semester, which is going to be what notes did Taylor Swift play in a given song? So we want to answer, how do we store the music? How do we then figure out from the music that we've stored what the given notes are, and then going from those notes back to some representation that we can easily work with. And with that, we'll end a little early today, and I will see you all tomorrow.